Alright, so today we're going to be going over we're going to go over what a derivative is, but more so in kind of like a basic form. It's like the first proof you'd be introduced to when taking your first calculus class. So before I get on to explaining what exactly a derivative is, I think it's important to go over slope first. So say I had a Cartesian coordinate plane and we had a function, we'll just say y equals x, and it goes directly through the origin. And we wanted to find the slope of this function, so we could pick 2 points. We'll call this point here just x sub 1, y sub 1, and this point here x sub 2, y sub 2. So in order to find the slope, which keep in mind the slope is going to be consistent since it's a linear function throughout the entire graph. It's going to be a constant. So the formula for that is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So that's going to be a pretty important formula. Now we're going to move on. So if you haven't tried this with other functions than first order functions or linear functions, you'd notice it doesn't work. And the reason why it doesn't work, let's say we look at a parabola. Draw this guy here. Excuse my interrogation room lighting. So we'll look at y equals x squared. It should look something like that. The arrows. It'll look something like that. And let's say we wanted to find the slope between 2 points. We'll use green for that. Okay. So let's say we wanted to find the slope at this point and at that point, right? Well, if you notice, and I should have drawn this a little bigger, if you draw a line between these 2 points, there's a small gap right there. And if you also take a step back and look at the slope of the overall function, you can tell the slope on the left side of the y-axis, it's going on a downtrend. It's on a downward trajectory, which, you can tell means that this is likely a negative slope. And on the right hand of the y-axis, it's moving upward or at a positive slope. So there's no way you can get a constant slope that's going to apply to every single point on this graph. However, that's where derivatives come in. So let's look back to this secant line I drew here. And all a secant line is a line that passes through a function at 2 points. And in this case, it's this point and that point. So we're going to do the same thing we did before. So we're going to attempt to take the slope. We're going to say x sub 1, y sub 1, and x sub 2, y sub 2. Okay. Now I'm going to stop here, and we're going to take a moment to look at an analogy to kind of help visualize what I'm about to do. So say we were driving a car, and we were trying to look at the distance. So say we were going 60 miles per hour. So our distance, the y-axis is going to be our distance, and the x-axis, we're just going to call it the time axis, is going to be our time. The units for time are going to be an hour, and the distance is going to be in miles. So if we're going 60 miles per hour, let's say we drove for 30 minutes. So after driving for 30 minutes, it's going to be 0.5 hours, and the distance is going to be 30. So this is one aspect of our movement, but we could also look at, say, our speed, or rather velocity. So this is also time equals 0. Note that the variable t applies to both of these one-dimensional graphs. And let's say at this particular point, since we know, we'll take the same exact point in time, and let's say our velocity was 60 miles per hour constantly throughout the entire drive. Draw that here. So this is an instantaneous snapshot in time. We can look at time equals 0.5 or a half an hour, and we could say at that exact point in time, if we froze time, we are moving at 60 miles per hour. And why I showed you that is because for any function, you can do the exact same thing. So let's say our velocity wasn't constant, right? Let's say we got on the highway, we moved at 65 miles per hour, and then we got on like a normal road, and it was like 40 miles, and then maybe we were driving through a school zone, we had to go 20. So at any point in time throughout that drive, you can look at the instantaneous speed, the speed we're going at that exact point in time. And that's what a derivative is. A derivative is the instantaneous slope or rate of change at a particular point. So let's go back to these two. So what we're going to want to do is find a tangent line, not a secant, that touches y equals x squared at one exact point, so we could find the rate of change at that exact point. And what we're going to do is draw a bigger graph first. So give me one moment. Redraw our parabola. Ooh, that's a good looking parabola. Okay. Here's our point here. X sub 1, y sub 1. And here's our point here. X sub 2, y sub 2. So, and I'm going to draw our secant line. Draw it in red. Alright, so that's our secant line. So what we're going to do, since we want to only touch the graph at one point, not two, because this doesn't make any sense, we're going to look at the distance on the x-axis between our first point and our second point, and we're going to call that h. So what we want to do is we want to drag this point down the function as we decrease h, all the way until it completely overlaps that point. And I'm going to do another change. So I'm going to rename our points. Instead of x sub 1, y sub 1, I'm going to call them, oops, we're going to call this one x, we're going to call this one f of x. So that's just the same thing. F is a function of x. F of x is the output of x. And we're going to call this one x plus h, because if we have our point here, x comma f of x, and we're adding h on the x-axis, then that also describes this point here. And we're taking the input of this, x plus h, and getting an output. So we're going to call that f of x plus h. And here are our 2 points. So now what we're going to do is we're going to use our good friend from algebra, the slope formula. I'm going to say m is equal to f, and keep in mind this is still x sub 2, y sub 2. This is x sub 1, y sub 1. We're going to take this guy, f of x plus h, minus f of x over x plus h minus x. I'm going to erase that for now, and you'll see why in a second. We're going to rewrite this guy. We're going to just do some canceling because positive x, negative x's are going to cancel out. So those just disappear. And this is what we're left with. So there's one last thing we need to do, and I assume you're familiar with limits if you're trying to research derivatives. So you're going to take the limit as h approaches 0. And if you look at our little visual here, this is describing the process of shrinking this distance between these 2 points, of bringing this guy all the way down to overlap on top of that guy. Whereas this part is the slope of the tangent line that we're going to end up with once we apply the limit. Our line, I'm not going to draw it out because I already have a bunch of stuff going on here, should look something like this, where it only touches that point and it veers off into positive infinity and negative infinity. And this is the limit definition. So if we want to actually apply this, I'm going to show you an application, and we're going to use it on the function we just used. We're going to find the derivative of that function. So here's our function, y equals x squared, and here's our limit definition, the limit as h approaches 0 of f of x plus h minus f of x over h. So I'm going to rewrite this, and we're going to call this f of x. So f of x is equal to x squared. So what this is saying, we're going to grab our parabola here, and we're going to plug in x plus h into our function, and then we're just going to subtract by our function over here. So the limit as h approaches 0 of x plus h squared minus x squared, and just to reiterate, we're just plugging this guy, x plus h, into that guy, over h. Get rid of this, it's in the way. Alright, so now your goal in taking the limit here, because if we plugged in the limit right now, we're going to get 0 over 0, which is the indeterminate form. And again, if you guys know anything about limits, if you get the indeterminate form, that just means you need to do some simplifying. So that's exactly what we're going to do. I'm going to say this is equal to x squared plus 2hx plus h squared. That's just the expanded form of this factored form. And then minus our x squared from here. Ooh. I don't think I have enough room for that. So this is equal to the limits as h approaches 0, x squared plus 2hx plus h squared minus x squared over h. We can cancel the x squared and the negative x squared out. That leaves us with the limit as h approaches 0 of 2hx plus h squared. And I think you can see where this is going now. We factor out an h. This becomes 2x plus h over h. These cancel out. That leaves us with the limit as h approaches 0 of 2x plus h. And now this is really easy. All you do is you direct substitution, you plug in 0 for h, and you get 2x is the derivative of x squared. So let's say we wanted to find that instantaneous slope that I was talking about before at x equals 4. And here's the notation for derivative. It's just f and then an apostrophe there. That's, yeah, and that's called f prime of 4. If you're taking the second derivative, which you can do, which is just the derivative of the derivative, in which case that would be 2. Why I know that? There are multiple derivative rules to make this process significantly easier. Because you could imagine, say we had x to the power of 10, and we tried plugging that into here, well, that would be x plus h, the quantity of x plus h to the power of 10. You would not want to expand that, but that's for another video. So yeah, you plug in 4 into the derivative. The instantaneous slope of x squared at x equals 4 is 8. And that's pretty much it.